Hey, welcome to the Engineer's Workshop. I never did post a finished video or a follow-up video on the Quincy compressor because I struggled with that initially before we had power at the shop. I had tried the single-phase motor and the generator did not have enough oomph to get the motor off its start windings, and it just tripped the breaker out. So I put the three-phase motor on and it ran fine with that. Then we got power, so took off the three-phase motor and put the single-phase motor on, and everything was great. It was making air, set the pressure switch, kicked off at 150 psi, no problems. Well, the other day I came out to do some orbital sanding on a project for the house, and when I started the compressor, the motor spit out this little glowing arcy thing out of the ventilation slots at the back, and that's, well, that can't be good. It came up and ran, but I thought, well, maybe just the contactor for the starter arced or something. But the next time that I went to start it, all I got was a hum. So the starter contacts either fused or are no longer making contact, bringing the starter capacitors in, and that motor won't start. So I did some rooting around. I have actually a couple of old Fincor VFDs. These were single phase, 5 horsepower VFDs. Very old style from like 1981 that instead of a sine wave output, they output a square wave, 3 steps, positive and negative, just with transistor switching. But so it's a VFD. It runs a motor, so I'm not worried about high frequency interference for sensitive electronics out here. So I'm going to go ahead and use one to drive the 3-phase motor on the Quincy, and I'm also going to set it up with one of these nice Ashcroft pressure switches. This is a dual micro switch, fully adjustable pressure switch with a gauge isolator. There's a diaphragm in here, and the upper part of this is filled with glycerin, so you can have any nasty corrosive process fluid on this side, and it isolates the instrument from that, but it still transmits the pressure, whatever you got on the downstream side, to the instrument itself with a clean glycerin. So had that thing for about 20 years. It's finally found a home on the Quincy. I'll show you how I hook this up, and I'm going to use this to switch between 60 hertz, in other words full speed running, and a reduced speed, maybe 40 hertz, when the compressor is up near its set point pressure. And then at the set point pressure, the Quincy has a centrifugal switch to unload the valves. So basically it will cycle off of that centrifugal switch, or rather it's a pressure switch, to load and unload the compressor, and it'll run at a reduced frequency when this pressure switch is closed. And then if the pressure drops further, contacts will switch here and bring the compressor motor up to full speed. So it should be pretty slick. Almost like a proportional control, but it'll be just in several steps. And I'll throw in some old video that I have of troubleshooting that pressure switch for the compressor. And this will be the final configuration of that compressor. And I'm going to go ahead at this point and sandblast the belt guard and get that installed. But I wanted to show you the hookup for this and the logic that will drive the control circuits for this. And should be a pretty interesting video for those who want to geek out on controls and air compressors. So we'll cut to the video now. After finishing my air line, doing a real nice connection with flexible stainless steel hose over to the Quincy compressor, I have an issue. Last time I ran it, when it started up, I saw this, I wouldn't call it really a spark. It was like a little glowing piece of something came out of here. And I mean, it started up and ran, and it ran just fine, but what must have happened was the starter contactor must have melted off, or something happened with it, because it won't start anymore. So I'm not in the mood to take the motor apart. It's not a particularly great motor. It's a Leeson 5-horse motor. Since I have the 3-phase motor that was redone with new bearings and painted at one time, I'm going to put the 3-phase motor back on here with an inverter. Let me show you the inverter. I find this kind of funny. The Fincor VFD, which is 5 horsepower or 4 kilowatt, from 1981, and its replacement, which the box that it came in almost weighs more than this VFD. This is your kind of generic, hate to say Chinese, but it's Chinese, 4 kilowatt VFD. Supposedly does the same job, but this guy, 30 some pounds, the entire back plate is a heat sink. I don't know how this thing dissipates its heat. It's got a little fan, but my gosh, I'm just amazed. If it does the same job as this, then boy, they sure are using a lot less resources making it, but we'll see. This is the one we're going to hook up for the compressor. Been a while since anybody's seen one of these. This is the Heathkit Design Experimenter ET3100. I built this when I was probably 15 years old. So that makes this about 40 years old. It generates positive and negative voltages. It has a 30 volt reference frequency at about 60 hertz. And it has both sine and square wave with 2 different frequency ranges, and a little breadboard area, a couple of potentiometers. But what I'm going to use this for is to simulate a resistor bridge that the VFD uses to input speeds that are lower than full speed. Let me show you how this works. This point is the measuring the voltage across the supply, and we can adjust that and try to get it as close to 10 volts as we can. 10 volts is our reference voltage in the power supply of the Fincor DFV. So there we are. So that's 10 volts. Now basically, as we proceed across this resistor chain, the voltage is going to start out low and keep climbing. Here's a neat little device. These used to be around everywhere. It's a resistor color code helper, and this thing is from D&J Electronic Supply, Warren, Ohio. That's my hometown. And here's how old this thing is. Phone 3721-6. I don't remember 5-digit phone numbers, but I do remember party lines. And of course, Warren, Ohio, there's no zip code because zip codes were invented sometime in the late 60s. And what you do is you take a resistor that you don't know what the value is, and you look at the color bands. And so this one is yellow. So you find yellow, 4, and then the second color band is purple. And there's purple. And the fourth color band is brown, and there we're on brown. So yellow, purple, brown is 470 ohms. If you wanted a much higher resistance, you could find a yellow, purple, red, which would be 4700 ohms. But basically what I need to do is I need to take a chain of resistors that adds up to about 5 kilo ohms. And so I've got a number of 470s, the yellow, purple, brown, and then I've got a couple of 1K. And a 1K resistor, let's see, is red, black, excuse me, brown, black, red. So brown, black, red is 1000 ohms or 1 kilo ohm. And those chained together will give me enough discrete points, and I can tap off of one of those points and get a percentage of full speed on the VFD. Okay, I made a spreadsheet that had the resistors all chained up in the same order as what's on the little experimenter breadboard. And we have our reference voltage, the ground at 0, and set to 10 volts. And what I'm going to do is I'm going to read the voltages across each one of those resistors and put it into this spreadsheet. So my first resistor, which is a 1K, I have 1.99 volts. And that tells me that's going to give me an output frequency of 24 hertz, which is 40% of full speed. And then I did all the math with the ratios of the motor and the flywheel on the compressor, and that's going to give me about 214 RPM. So the next resistor is another 1K and gives me 4.04 volts. So that's a 55% of rated speed, 296 RPM. And the next one, 6.09, 71% of rated speed, 378 RPM. The next is 7.11. 78% of rated speed, 419 RPM. 8.14, excuse me, 8.16 volts. 86% of rated speed, 461 RPM. And 9.05 volts. 93% of rated speed, 497 RPM. And then if the speed signal, the reference, were tied at the 10 volt, at the high end of the resistor, that's 535 RPM on the compressor. Three-phase power looks like this. You got a waveform, goes positive, goes negative, that's one cycle. Simultaneously, you got another phase that does this. And you've got a third phase that's like this. So you can see at any given moment, you've always got voltage and power going to the motor. Now let's look at single phase. That's single phase power. Starts at 0, peaks, comes back through 0, negative, and back to 0. At these points, there's no voltage, so there's no power going to the motor. A 5 horsepower single phase motor, when you put an ammeter on it, will draw close to 20 amps. A three-phase 5 horsepower motor, same voltage, draws 6 amps per phase. So it's divided into 3 separate circuits. But since you're drawing 6 amps in a wire versus 20 amps in a wire, you don't need as big of a wire going to the motor. Now these inverters, today's inverters generate a true sine wave, and that's the best way to do it. But in 1981, the Fincors, they simulated a 3-phase waveform by using transistor switching. So what the Fincor does is it turns a transistor partially on and does that. And then it turns another transistor fully on and does this. Then it turns another transistor on and does that. Same thing in reverse. So the output of the Fincor VFD is actually a stepped square wave. That's the simplest way to do it. It simulates the true sine wave AC waveform by using simple transistor switching. Now, at this point, the transistor is fully on, and when a transistor is fully on or saturated, it has very low losses through the transistor, and so it doesn't conduct much heat or generate much heat. But in these points, the transistor is partially on, or it's operating in what's known as its linear region. And so when it's passing current, it is also dropping voltage and therefore generating a lot of heat. So during 2/3 of the cycle, like 4 out of 6 steps, these transistors are generating a lot of heat. And then when they go fully on, positive and negative, they don't generate as much heat. That's why this VFD has such a huge heat sink on the back. So basically you have a set of transistors to do this, another set to do this, and then you have a negative, mirror image set that does the negative partial waveform, and a 4th set that does the negative full voltage waveform. And they just turn on sequentially, and let me show you what that looks like in slow motion. I want to give you a peek inside of this. We've got input fuses. These on the top side are braking resistors. And then we got the capacitor bank behind a fiberglass shield. And then the boards, the output transistors. So we have 3 phases and then positive and negative. So it would be phase A positive, phase A negative, B and C. And then these are the driver boards which generate the sequencing of the transistors. The control board is mounted on the door. There's various pots for adjustment of minimum frequency, minimum speed, voltage limit, voltage boost, max speed. A couple of them I've never adjusted. I built my resistor bridge on a terminal strip. 0 volts, 10 volts, and then low, and low speed. We'll fire it up, take some current readings. That's pretty tolerable for background noise. I mean, if I'd have to guess, there's only maybe 40, 50 decibels. You can definitely converse over top of it. Hope you enjoyed that rundown on how we got the Quincy configured to do 3 stages of speeds. And at the end of this, if you want to continue watching, I'll show you how I rebuilt the VD pilot and put the new diaphragms in the discharge valve here. Got to do the belt guard. I was tempted the other day to reach in and close off my valve here, and I got to keep reminding myself, do not do that from the other side. So I've got to get that belt guard on and protect myself from stupidity. But next I got to get back on the trolley beam. So I think that's what I'll be working on next, and appreciate everybody's time watching this. Stay safe. That's it for Engineers Workshop. Okay, so everybody's going to be very happy to see this. This is a all stainless pressure hose. It's got a corrugated stainless inner and then a braided stainless outer. It's rated for about 700 psi. It's got good temperature characteristics at 600 degrees Fahrenheit. It only derates about, I don't know, 7-8%, so it's good for like 600 psi at 600 degrees Fahrenheit. So we're coming off the compressor with a 1¼ union elbow. This is the old swivel fitting, the 1¼ NPT swivel fitting. I had to put that on because I had just not quite enough length with the hose to come directly from the T into the street elbow, which I had intended to do. So this gave me an extra about 1.5 inches. Also gives me a little bit of a S-curve in this, which is good for the temperature expansion. And you notice I'm plugged back here because we did have the copper line coming up to feed the VD valve assembly, and this is the low oil pressure sensor that will both unload the compressor. So anyway, I should have seen this happening, but piped in here, my intention was upstream of the check valve, so when the compressor shuts off, this will not see the tank pressure, and therefore, because I've got a tiny leak across this check valve, this won't bleed down. My tank pressure will stay up to where where it was pumped, because I don't use this every day and I want to maintain that that compressed air. So what started happening, and like I said, I should have seen this, was while it was running, the compressor would come up to pressure. The VD pilot would say, okay, going to kick out, so we're going to pressurize the valves. That unloads the compressor, which unloads the pressure in here, and then the VD says, oh, time to make compressed air again, and it would load the valves back up. And then this was happening about 2 or 3 times per second. So this thing was just going, constantly cycling on and off, because this point where I was tapping the pressure was getting discharged by the valve. So this has to be fed by tank pressure. Let me bring you over here. Well, I'm in here and I've got the sump wiped out. There was really no sludge. A little bit of darker oil where you got some accumulation. I assume that's just slow wear of the cast iron surfaces accumulating in the oil or dirt. But I'm going to go ahead and put new oil in this and put the cover back on. Well, there's a sump full of clean oil. This stuff's clear. And we're really only about halfway up the dipstick. It definitely could use, I'd say, 2 more quarts. So, 2 to 3. This thing probably holds 8 quarts. I bought 5, and 5 is good enough for a startup and to run it. But I'm going to get a couple more quarts on the way, maybe 3. Don't get to use this very often, but it does come in handy for things like this. Just a little bit of crustiness. I'll hit the wire brush on that. Now that one is definitely probably frozen in place. So we'll have to do a little bit of scraping and see if we can get this one freed up. Okay, it will rock. Now it's just a matter of how I'm going to get it out. I don't know why these have to be so close fitting. Let's wire brush that. trying out a new strut mounting system from McMaster, my favorite place in the world. Basically, it's these caps that you hammer into the end of the pieces of Unistrut. You cut the Unistrut about 1.5 inches shorter than your space, and this mounts inside an I-beam, so it will jack these barbs in opposite direction and clamp against the insides of the I-beam. So first step is to hammer them into the ends of the strut. You know what? I have it backwards. I see there's a right way and a wrong way, and I did the wrong way. That's the right way. And they're definitely not going to come out. Let's put a couple of strut nuts in here and see how it fits. Since I have a wall that's vertical, I kept the square factory end, and I'm going to use the two barbs over there, and I have one barb on this end. I just have to kind of eyeball this to keep it level. Let me step back and see how that looks. Looks pretty level. It is definitely biting. and measure up for the upper one. Okay, always the fun part now. I'm leaving these two fasteners in place with the hopes that I can lift the VFD into position, slide it onto those tabs, and then start those with the screw gun, because this one is heavy. I don't think that's coming off of there. Pardon my reach. Here we go. Best bet is probably to feed up into this one for power. Since that one's 3/4 inch conduit, maybe I'll use that. Or I can just go down to 1/2 inch conduit. I have enough of both. I think that's what I'll do. I'll just use the 1/2 inch conduit here. And use THHN individual conductors